and looking at stoichiometric problems that require more than just one step in the math to solve. Okay? So I like to start here with reading and identifying what I need to achieve. So quick recap here. We have our expanded mole diagram. The left-hand side, this is where we start our math. So we figure out which quantity we're starting in. And then the right-hand side is what we are trying to calculate. Where are we going to end up on the far side? So when I take a look at the problem I'm given, it says, what mass? So that's what we have to figure out. So this is where this mathematical problem needs to end, and it has to end in the mass circle. So we have to get all the way there to the mass circle. When I keep reading, I need to determine the mass of H2O2. So I'm going to label this as H2O2. Now I have to figure out, well, to get to the mass of the H2O2, where am I starting? So when I continue reading, I see a number of 11.2 moles, and I keep reading, and the substance is not H2O2, but O2. So that means I'm starting on the other side. So I'm starting in the left-hand box of moles, and the moles belong to oxygen, and I have 11.2 moles of oxygen. I need to get to H2O2. So now I just need to follow the road path. So that means I need to first get to moles of oxygen, and I need to cross over. Well, when you cross over from one mole triangle to the other one, this does not belong to oxygen anymore. I need to get to moles of H2O2. And then from there, when I have set myself up mathematically, now I can go from moles of H2O2 to the mass of H2O2. So let's just think about this mathematically and get ourselves set up with the correct numerical setup. So it's very important to keep your work nice and neat so that you can track what you're doing mathematically. So I know that I'm starting off with 11.2 moles of O2. And when I leave this, step one is I need to get to here, moles of H2O2. So I'm leaving moles of O2, and I'm heading to moles of H2O2, and I'm leaving behind and want to mathematically reduce out, make moles of O2 disappear. So with that set up, I am now here. That's step one. But I'm not done because I need to get to grams. So now I'm on the second roadmap, or the second line, so that means I need another equivalence. And so now I'm in moles of H2O2. I want to get rid of moles of H2O2. And I want to end up with grams of H2O2. So now mathematically, when I look at my labeling, I have moles of O2 times moles of H2O2 divided by moles of O2. So since I have moles of O2 down in the denominator and moles of O2 up in the numerator, they are gone. So it's reduced to 1. Now I'm left with moles of H2O2 times grams of H2O2 divided by moles of O2. So mathematically, in the second step, my moles of H2O2 also reduces because I have one upstairs, one downstairs. So mathematically, I'm now left with grams of H2O2. So now here's the thing, is I have to figure out, okay, what kind of information, equivalence information, goes in the first set of parentheses versus the second set of parentheses. So my first set of parentheses, number one, this is step one, where I'm going from moles of O2 to moles of H2O2. So because I'm actually changing the identity of the substance, that comes from the balanced reaction. So let's go up and take a look at it. Our reaction, we have to double check, is it balanced? I see 2 H's on the left, 2 on the right. That's good. I see 2 O's on the left, but I see a total of 3 on the right. So the oxygen count is not okay. So I'm going to work with this idea. Since this is an odd number of oxygens and my other two substances have an even number, I'm going to put a coefficient that will make my oxygen count from an odd number to an even number. I find that easier to work with. So by putting this 2 here, it makes this oxygen count 1, but makes it 2. So now I have 2 oxygens here plus these 2 oxygens gives me a value of 4. Now I only have 2 oxygens on the left, but if I put in a coefficient of 2 out in front, 2 times 2, now my oxygen count is 4. And working and balancing the oxygens by putting in this coefficient, my hydrogen count is 4. And when I go to the other side, I wasn't even paying attention to the hydrogens, but I put a 2 there, and 2 times hydrogen subscript makes it 4. So just by taking care of the oxygens, I balance the hydrogens. And I understand that my coefficient here in front of O2 is 1. So when I'm looking at this problem, okay, paying attention to the details, I know that I need information about O2, and I need information from the reaction about H2O2. So these are the numbers, the coefficients that I put for the balanced reaction. So since H2O2 is on top, look at its coefficient. So for every 2 moles of H2O2, according to this reaction, it requires 1 mole of O2. Now, here in the next equivalence, I have moles of H2O2, and I need to get to mass of H2O2. And I know that I wrote over this, but if you look carefully at it, to go between the moles of H2O2 and the mass of the H2O2. So notice this time the identity of the substance is staying the same. So now we're back to what we did before. It's a matter of the GFM. So I need to calculate the GFM of H2O2. So I have 2 oxygens, each one contributes a mass of 1, plus 2 oxygens, each one contributes a mass of 16.0. So the GFM of H2O2 is 34.0 grams. So every 34.0 grams of H2O2 equals 1 mole of H2O2. So here I need to use the GFM relationship. So 34.0 grams of H2O2 equates to 1 mole of H2O2. So now that I have all my number information, now I can put it into the calculator. 11.2 times 2 times 34. So when I put this into the calculator, my calculator answer is 761.6. But I have to think about sig figs. So my starting quantity has 3 sig figs, so I can only keep left to right 3 digits. This would make the 1 round up. So probably the best final answer here would be 762 grams of H2O2.